Welcome everybody. I want to first maybe spend a couple of words. So Anupam and I were sharing an office in Boston, and I think it was basically he taught me how to play squash. I love squash now. He sort of kicked my ass. Hopefully this is okay for the recording, and we really had a lot of fun. And I think I mean, as you're gonna see also in the structure of this mini course, there is going to be a very nice interplay between, coherent structures, which is a way to understand the dynamics of complex systems, and also when, on top of that, what are the forces that generate this dynamic. For instance, I don't know, viscoelastic materials, turbulence, etc. If you combine these two aspects, you can do way more. You can try to control these coherent structures. You can try to maybe design particular force structures that will give desired properties. So there's going to be basically a very nice synergy here. So I mean, there is no way I can really tell you about coherent structures in whatever 1 hour. So the way I was designing these slides was pretty fluid. I really want you to stop, and if there are things that are unclear, we can just go a little bit together here on the boards. Namely, I don't really have to go through all the material that I have on the slides, and of course, there are a lot of references and now even books on coherent structures. So this is just to give you a general flavor of what they are, how they are getting extended, and how you can actually extend them for your own problem. So before I start, basically, I want to maybe give one slide overview of what we do in my group, just to present myself. In my group, basically, we do two things. In the first part of research, or one research direction is trying to understand what are the patterns in nonlinear dynamical systems. So let's say, for instance, you have atmospheric flows or oceanic flows or flows on of liquid crystals, so active nematics, or multicellular flows. These are basically flows of cells. If someone basically measures these flows and you don't know anything about the forces that generate them, because this is how you start. Usually you don't know the equations. The equations for cells are basically very much unknown. The equation for liquid crystals are becoming more and more known. The equations governing atmospheric oceanic flows are basically partially known, but there are a lot of uncertainty. Or in the atmosphere, similar story. But then you can ask, I measure these very complex flows, what are the organizers of these complex flows? And then you can sort of do, coherent structures is another, for instance, title for this first part, is a way to understand this complexity and condense it into the essential units, okay? And the interesting part here is that this is basically, these techniques, because they use the language of dynamical system and geometry and mathematics, they don't really care about scales. So you say, okay, this is my flow. I don't really care about forces and asking, okay, what forces are more important over this time scale or spatial scales? You don't care about it because you already measured the velocity. That's already the output of the forces. So you measure that and you ask, where are the interesting features? For instance, are there exceptionally coherent vortices in the atmosphere? Are there basically short time attractors or traps that tell you where floating objects, including people, will accumulate, or where, for instance, are there transport barriers in liquid crystals, naming regions that don't mix with each other, over which time and where are they in these liquid crystals? Or for instance, you can also ask, where are attractors or regions where cells will converge in a distinct way, or where are regions where cells will separate mostly in a distinct way in embryos or tissues? And the second part, instead of research, is more trying to understand and use basically force-based principles. So if you want to understand how an ensemble of cells generates basically a formed body, you have to understand the forces that shape these cells. So there is going to be, force balance. Then you also have to understand differentiation. How do cells transform from general or pluripotent cells into differentiated cells? I don't know, neurons, bones, muscles. This is another complicated dynamics. And also you want to understand how do cells to understand where they are in the embryo. How does the embryo pattern itself, right? So there is pattern formation, and the synergy of all these physical and biological processes will basically, in synergy, they will tell you, or will try to elucidate how an ensemble of cells will generate basically a formed body. Okay, so that's basically what we do in my group today. I want to focus on the coherent structure part, and I don't know basically your background, so I'm gonna just do a very elementary overview of what is a dynamical system. Do you know, guys, what is a dynamical system? Who does know it? I'm not gonna ask what it is, but just for me to understand. So basically, did you guys read the book of Strogatz, linear dynamics, or okay? Anyways, so basically that's good. So we start and we are basically on the same page. So a dynamical system is, and this is very important to understand coherent structures, but a dynamical system is basically, roughly speaking, is a set of two things. It's a phase space. You have to think of this as a set of axes that will basically specify your coordinate or the coordinate of a point. And when you specify that point, that's basically the state of your system. Okay, so let's say this is basically can be very high dimensional, so there is going to be x1, x2, x3 to xn, and can be also infinite dimensional. But eventually, once you specify the state, that means the state of your system is uniquely defined. Okay, and then there's going to be an evolution rule, which is going to tell you, is going to propagate basically this state, into the next position. Okay, that's basically a dynamical system. So it's very important that you appreciate both of them. So the phase space and the evolution rule that is going to tell you how you move from time initial, t0, to time t of this particular state. Okay, so this, of course, it's a very general language. So you can have three-dimensional flows in the in the air. This is a tornado. If you want to understand how fluid parcels of air, or how parcels of air will move, this would be x1, x2, x3, and then I start with the fluid parcel here, and then the flow, the wind is going to just advect basically this fluid parcel and go somewhere else. Okay, this could also be the space of functions. So basically, it could be an infinite dimensional space. For instance, if we think about the temperature profile in this room, to understand temperature profile in this room, you have to give me infinitely many points, temperature at infinitely many points. Let's say now we set this temperature at the initial time, and you open the window, you basically refrigerate the room, and then there's going to be the evolution of this temperature, right? So that would be basically a situation in which this is the initial temperature profile, that's the final temperature profile, and this would just be, infinitely many axes, because the temperature is a function. You can think of this as the basis of the Fourier basis over which you project the scalar function. Or for instance, this could also be your brain, right? The brain is made of thousands, or I don't know, maybe millions of neurons, and every neuron is basically going to have a particular level of activity, and therefore I'm going to have neuron 1 is going to have this level of activity, neuron 2 another level of activity. So eventually the brain is going to be a point in this phase space where the axes are just the neural activity, and then eventually I'm moving, and the brain just has a particular trajectory of this activity. Or
So basically, the dimensionality is a choice. Like suppose even for neuron, usually they're long, so there could be gradients in activity. So you can choose like whether you want to look at integrated quantities.
Yeah, that's good. That's good. That's very good point. So it's very hard. I mean, it's not an easy task to understand what is the phase space of your system, right? As Anupam is saying, right? But let's say, for instance, you say, okay, neuron is so the activity of a neuron is a continuous function. So you can say, it is a continuous function. So it's like a neuron 1 is gonna, I don't know, is as activity x, activity x1, x1 tilde, x1 double tilde, etc. Yeah.
But it's a choice what problem we are interested in.
Exactly, yeah, it really depends, yeah. And or for instance, you can also have flows of cells in an embryo, and this would just be a three-dimensional phase space where this is the initial position of a cell, and the later time you're going to see the cells at a later position. Okay, so whenever you have a dynamical system, as general as you want, eventually the trajectories of this dynamical system will look like this. Okay, it's a kind of a spaghetti plot, okay? And the more you increase in dimensionality, the more it's complicated to understand if there is a pattern or a structure. So coherent structures, what they try to do, they try actually to condense these spaghetti plots into structures that will simplify the dynamics. For instance, I don't know, if I start here, these two trajectories, they seem apparently, pretty much unrelated, but eventually, if you compute was this on? No. So if you compute basically coherent structures, you can say, okay, these two trajectories, they are landing on the same attractor, so they will converge to this one particular attractor. These two trajectories, they are basically separated by a repeller, and therefore they will go to different structures in this phase space. And similarly, this trajectory and this trajectory, they are apparently very different, but they will converge to the same attractor. This is just a pictorial example, but in general, you have to, the way I think about it is that now once you have these guys, the coherent structures, you say, okay, I know a simplified but clearer picture of this dynamic, okay? And then I can do prediction or analysis on them. Okay, so basically the way we think about it is that coherent structures are sort of, a skeleton or a coherent skeleton of trajectories. Now this could be a velocity field or a general dynamical system, and if you want, you can also have another pictorial example, which is, let's say for instance that you have a velocity field in 2 dimensions now, and you color this velocity field with a particular, pattern, let's say constant color in y and a gradient of color in x, and then you let this evolve passively with a velocity field, and you're going to get basically, this is a 2-dimensional turbulent velocity field, and then you're going to see basically that there is a very strong patterns that this velocity field is generating once you, pattern this initial condition in a particular way. And here you can ask the same things. Are there particular patterns or coherent structures that shape this apparently very complex, picture? Okay, so the motivation I already told you about. Again, this applies across scales, and you want to understand, what are the organizing patterns or of fluid motions, floating objects, cells, etc. In a particular dynamical systems, and why you want to do that is because, again, in most of the experiments, let's say for instance in these cell experiments, you just don't know any forces. There are some cases in which you have no idea what are the forces that are driving this cell, but still, can I apply this machinery? The answer is yes, because from the velocity field, you can just deploy these techniques and identify all these patterns, okay? They are scale-free. Again, as I said, they don't really care about the scale, and you can also apply them with, when the forces are unknown. And the challenges, or I would say, maybe the even more interesting benefits of these structures is that you don't even need to know the equations. When you do actually calculation according to, whatever elementary structures or whatever elementary notions you have of dynamical systems, you open a book, usually they say, okay, this is the equation you start with, you start looking at, particular techniques to attack these equations, but what do you do when you don't really have equations, but you just have data? You cannot use these structures. And most of the theory that have been developed in dynamical systems were developed for systems that were autonomous or time independent, or that had some particular regularity. They should be time periodic, quasi-periodic at most. But in real life, basically, none of these structures are like that. They're just generally time dependent. So most of these techniques that were originally developed, they don't really apply for general systems or real life systems. Okay, so what we're gonna do? So what is really the philosophy to identify coherent structures? There are basically 2 things that you have to do. You have to define a coherent principle. Okay, so we're going to look at Lyapunov exponent later, but I want to show you in this set of slides that there is a lot of possibilities to define coherent structures depending on what is coherent for you, for your problem in physics, biology, neuroscience, I don't know, AI, etc. So you define a coherent principle. For instance, you say, okay, I want the regions in the flow that are the most attracting, so that's the coherent is attracting. And then once you formalize this functional, you want to maximize. And then you say, okay, now I'm going to find the structures that maximize this coherent principle. Okay, but this the way I'd like you to think about coherent structure is something more general. For instance, if you want to understand if a region, a part of the brain is synchronizing with another part of the brain, okay, then you would look for a coherent principle that is based on synchronization. I mean, the notion of coherent structures based on synchronization, it's not there. Nobody has done it. I tried to do it. It's very complicated to define synchronization very rigorously, but this is a very open-ended process, right? That you say, okay, now coherence for me synchronization is attraction, repulsion, vortex-type coherence, etc. So this is the way I want you to think about coherent structure in a general sense. Okay, so then, I mean, there is the types of coherence, which is going to also come up in the next slide, but there is a time of coherence. Yes?
So like, if you think about synchronize, so usually the idea I have for coherence is they're long-lived, right? And that's how I have.
Yeah.
If you think about synchronization, so there could be oscillations.
We are going to go exactly to this point. It's an excellent point. Coherence, it really depends on the problem, on your need. Because I'll show you basically in a second that some structures are coherent, they're very important, but they don't have to be long-lived. Okay? So, for instance, if you have, I don't know, if you have two trajectories and you want to identify, are these two trajectories synchronizing towards a particular structure, right? That's a very natural question to ask. It's very hard to pose this mathematically, right? But I'm going to go back to here, and this is also related to this point. So basically, there is a notion of coherence, but there is also the time of coherence. Let's say, for instance, you say, okay, someone gives you a velocity field of the atmosphere, and you want to ask, what are the coherent structures? But the first thing you have to tell me is that, are you interested in what, hundreds of years? Are you interested in a month? Are you interested in, in a season, right? So the time interval over which you are interested in addressing this question is very important, and it really depends on your problem. Okay, I'll show you different examples in which basically you want to understand, coherence at different length scales. So if this coherence occurs over a finite time scale or a finite time interval, whatever it is, we are going to call them, finite time structures, or the so-called, Lagrangian coherent structures. This is basically, a large field of research that was led by George Haller and many other, people in the community. But the idea is that in this case, you're interested in a finite time effect of your trajectories. Remember here, these are trajectories of your dynamical system, the blue ones, and then depending on how long you plot this trajectory for, whatever is shaping them, these red guys, they will also have their own dynamics, right? But for instance, back to Anupam's point, so this is, for instance, a week in the atmosphere, a couple of weeks in the atmosphere that relate to the polar vortex. We're going to do this, investigate this example later this week. This is basically, 12 hours of an embryo that is developing. This is basically flows on the atmosphere. They're basically usually the time scales of, people are interested in their dynamics over, weeks, months. So finite time. But you can also ask, for instance, if someone wants to do flow control. For instance, there is the airplane, there is a wing, and then eventually you want to eliminate the possibility that the flow detaches from the wing immediately, right? Because if it detaches, it can cause, lack of aerodynamic performance, it can cause stall, it can also cause actually catastrophic events. So in this case, you want to react immediately. I don't care what happens in the scales of hours or minutes. I really want to do instantaneously, because if the flow is detaching, I want to reattach it immediately, right? Or for instance, in the context of search and rescue operation at sea, when there is an accident, and we are going to also see this example later in the week, when there is an accident, the Coast Guard wants to know immediately where to go. Now, they say, okay, now I have 2 helicopters, 3 boats, where should I send them? I have to react immediately, right? So these structures that attract people, I don't really care of the ones that will be attracting people over a scale of a month, because those are not the ones of interest in this particular context. And the same here. So this is basically the oil spill in the Gulf of Mexico. Several years ago was a huge catastrophe for our environment. And also here, there is this oil spill. You want to understand where should I go now immediately to bound this oil spill. So if the interest in this code base is basically over short time or infinitesimally short time, we call these structures basically Eulerian coherent structures or objective Eulerian coherent structures. And Eulerian just stands that you want to do this very quickly. So you can do it just with an Eulerian snapshot of the velocity field. Lagrangian means basically that you have to integrate trajectories, which is what we're going to look at in the next few days also. Okay, so Lagrangian and Eulerian is the time of impact of this coherence. The type of coherence is depends on your problem. Okay, so just a little bit of history on this. So I think when George Haller and collaborator were starting to look at Lagrangian coherent structures, I don't know, I think in 2000s, or more or less, so this is actually 25 years ago, when they actually got the motivation. Okay, so the motivation was actually going from what you actually see in the books. So if you go in the books, of a particular, let's say in the dynamical system 101, someone gives you a velocity field. We are going to do the exercise in a second now on the board. Someone gives you a dynamical system or a velocity field, time independent. What you're going to do, you're going to look for regions where the velocity is 0, which these are called the fixed points of the velocity field. And then let's say this is basically what I'm marking here with this picture. And then you're going to ask, okay, I have this fixed point, and then I will study if it's basically stable, unstable, or hyperbolic, naming basically if there are spiraling types trajectories around it, or basically saddle type trajectories around it. This is a saddle type. And then you actually compute the stable and the unstable manifold. Okay, so basically, let's say, so the stable manifold of these fixed points, the math is not important, but we're gonna just do it a little bit in the next slide. But you have this fixed point, there is gonna be a stable manifold, which is basically a region, or actually a curve in this case, where trajectories that move forward in time will eventually go to the fixed point. Okay, that's the definition of stable manifold or a fixed point. The unstable manifold is the opposite. So this is basically the regions where things will go away from the fixed points, or technically speaking is where trajectories will go to the fixed point if I run the advection backward in time. Okay, so basically now think about how do basically a blob of trajectory would feel this stable manifold and the unstable manifold. Well, if I place a blob of trajectory here, this guy is gonna separate from the stable manifold, and is gonna squeeze and get attracted to the unstable manifold. Okay? So these guys were saying, hey, look, wait a second, I can sort of think of this stable manifold basically as a repeller, because things that start very close, they will actually maximally separate. And then the unstable manifold, instead, I will think of it as an attractor, because things that were far away, now they will get squeezed basically to this attractor. Okay? So this, I mean, and the way to compute stable and the unstable manifold and fixed points, they just work for systems that do not depend on time. So x dot is equal to velocity of x, not x comma t. And this structure, strictly speaking, will have this impact on trajectories only if you wait infinite time. So if you want to understand what happens over an intermediate time, these are not the right structures. Okay, so I think we're gonna go back here, but yeah, the problem is how do you rethink these structures for unsteady flows, and how do you rethink of these structures when t is not going to infinity? Let's say, okay, I want to understand what happens after a one-time unit or 10-time units, okay? So I think this is the motivation that brought George Haller and collaborators and many others, I mean, in this community, you know, Gary Froiland, and this is a very large community and several references, they try to understand, you know, how do I really think of these structures in systems that are generally time dependent. Now, when I relax this condition, so this becomes generally time dependent, not just time independent. And when I'm interested on the effect on trajectories over a finite time interval. That was basically the original motivation. Questions so far? Okay, let's do basically a very simple example now. So this is basically a two-dimensional velocity field or an ordinary differential equation. Okay, I have basically x and y. This is the dynamics of x and y. Basically, it's of this form: x dot equal to f of x. And if someone gives you this velocity field, this you have seen it. Okay, and I don't know in which course, but something like that you've seen it. So what do you do when someone gives you this dynamical system or this velocity field? What do you usually do? Guys, try to guess if you don't know.
Find fixed points.
Good. Okay, so the first thing you do, look for fixed points. Okay, so you basically, okay, fixed points are the points, p or x tilde, where f goes to 0. And if you do the exercise, the fixed points of this guy is basically at 0, 0. Okay? Now, this is a very interesting thing, but you know, why people look at fixed points? Can I ask you this?
At that position, whether the system is stable or unstable.
Very good. So basically, you see, this is the way. When you think about coherent structures, basically, this is the way to approach it. You say, okay, you know, these equations, they could be way more exotic than this, right? But what you want to do is, and they can exhibit really a lot of complexity. So what you want to do, you want to say, where are my anchor points where I know how things, or I know how things will behave? The first thing you do is, okay, let me actually look for regions where things don't move. If I sit there, I'm not gonna move. So the first one is a fixed point. Okay, then, okay, so this, if you will, this is basically a type of coherent structures. It's a very simple one, but also very powerful because it tells you where things will not move. If I go anywhere in this space, x and y, I'm going to actually feel transported with very violent velocities and dynamics. Maybe I don't want that, but where are the fixed points are the regions where I'm not going to move. Okay, so after you calculate the fixed points, what do? You already said it, so you say, oh, I want to understand if I'm a little bit away from the fixed points, will I go back to the fixed point or will I go away? Okay. Okay, so, well, to understand that, basically, it's also, it's a little bit, laborious. Okay, so maybe we can just do it here. So this is a nonlinear differential equation. But I can actually copy this. I can actually copy this on the board.
Fine.
Yeah, this is. I'm just gonna do it here. So if I have this differential equation and I have a fixed point at 0, 0, now you can ask. So let's say we are here. Now this is the 0, 0 fixed point P, and then you want to ask, okay, if I start here, will I go away or will I go towards the fixed point? Okay. Well, to address this question, basically, it's already non-trivial because you want to understand it. How do you do? There are several techniques to address this question. The one thing you can do is let me actually study the linearization. Okay, linearize the system in this vicinity. And then I ask, I'm going to have an auxiliary system that is a simplified system compared to this one. And then I can study the stability of the linearized system. Okay? Okay, so that's basically what I did here. But I mean, are you guys all familiar with the linearization? Yes or no?
I think few of them
And I think at least
Okay, but okay, let's do it, guys. It's something very simple. So let's say you are here. This is point X. So this is basically general point X. This is P. And therefore, I'm just going to change coordinate and say that, I don't know, X. This is vector X, which is basically X and Y made of, scalar X and Y, is just going to be P plus a certain delta X, which is how much I moved from P. So this guy is a delta X. Okay? Then what do you do? Basically, I just expand this equation. I say, okay, x dot is equal to P dot plus delta X dot, the time derivative. And this is equal to F at that point. It's going to be X plus delta X. Sorry, P plus, this is going to be P plus delta X, because that was X originally, okay? Well, now this should hold only in the vicinity of P. So delta X should be much less than 1. Okay, so I'm just going to explore a vicinity of this fixed point. Okay, so then I can Taylor expand this because delta X is small, and I can say, okay, P dot plus delta X dot is equal to F evaluated at P plus the derivative of F with respect to X evaluated at P plus times delta X, leading order term in the Taylor expansion, plus order delta X squared, which is small, okay? Then you go immediately, you say, okay, P dot and F of P is 0 because P is a fixed point. So I already gained an immediate equation, which is the evolution equation for delta X. This tells me, look, the dynamics for delta X, which is the perturbation in the vicinity of the fixed point, is going to be the Jacobian with respect to X of F evaluated at P. This is a matrix, in this case a 2 by 2 matrix, times delta X. Okay, this is approximately equal because I'm just neglecting the rest. Okay, so now you have another equation, B, and this guy was A instead, my original equation. Okay, so the original equation was X dot equal to F of X. Okay, that's the nonlinear equation, that's the linearized equation in the vicinity of the fixed point. Okay, so then you want to ask, okay, my question is still understanding if I start nearby, will I go away or will I go back to the fixed point? Okay, and to understand that, the informations are basically, at least for the linearized dynamic, are in this matrix. So you do the linearization, you compute this matrix. These matrix for this particular systems are just basically 1, 0, 0, minus 1. Is it clear why? Because dx of f is nothing else than the derivative of the first entry of f with respect to x, which is the derivative with respect to y of the first entry of f, derivative with respect to x of the second entry of x of the dynamical system, and derivative with respect to y of the second entry of f. You evaluate this at the fixed point, and you get that. So these guys, dx of f1 is 1, right? Dx of dy of f1 is basically 0. Dx of f2 is basically 2x, and dy of f2 is minus 1. Yeah?
Also, I think that for the students that you can try it by yourself also, right? It's not like, no, I'm saying that they can try it themselves. It is
No, but it's just, I mean, of course, if this is too trivial, just pick up. But I want to basically, this thing will allow you to maybe understand where coherent structure originated from and why they are useful. Because if you go with this technique, you're going to get stuck pretty soon. You're going to see it here. So you go, you do this exercise, and then you're going to say, okay, so now I have this matrix, dx of p is going to be 1, minus 1, 0, 0, because I'm evaluating at the fixed point. So now with this linearization, what do you do once you have the linearization matrix? If you want to understand if the fixed point is stable or unstable.
Find find eigenvalues.
Good, yeah, very good. So good. So basically, you look at the eigenvalues, and they are already here because it's already diagonal. So you're gonna know basically that one eigenvalue is equal to 1 in the x direction. So the corresponding eigenvector is 1, 0. So it's the x-axis, and the other one in the y-axis. So the other eigenvalue is -1 associated to the y-axis. Okay. So what did we actually learn? We learned basically that if you would now study the dynamics of this system, just look on top for a second. Don't look at one below. So if I have x and y, and I'm looking at the dynamics of the linearized dynamic, this linearized dynamic is gonna have basically one eigenvalue that is positive in x. So in x, I'm gonna move away from the fixed point. This is called the linear unstable subspace. And this is gonna, instead in y, I'm gonna go towards the fixed point because this has a negative eigenvalue. This is the linear stable subspace. And therefore, wherever you start, you're gonna feel this dynamic in the vicinity of the fixed point. Okay, so I start here, I'm gonna go here. Start here, I'm gonna go here. Start here, I'm gonna go here. So the fixed point is unstable. Okay, those are basically the trajectories of the linearized dynamic. Okay, so that's good. So I already know that this system is linearly unstable near the fixed point. Okay, but then what happens to A? What happens to this general system? So the nonlinear system. Remember, this was basically x dot equal to x. Y dot equal to x minus x squared minus y. So if I have now that system, what do the trajectories do in this system? Okay, well, you have to do a little bit of calculation. It's not super trivial, but you can compute actually the similar, what are the equivalent of these eigenvectors of the linearization, this linear stable and unstable subspace. And if you do this exercise, you can actually compute that there is going to be for the nonlinear system, the black color, or what I use there in red. So the y-axis is going to be the stable manifold of the fixed point for the nonlinear system, and the unstable manifold is going to be a curve like this, which you can actually compute. Okay, and is actually of the form y equal x2 over 3. You can also do this with some techniques. And this is the nonlinear system. So this is going to tell you that now this system, if it goes with the dynamics of the nonlinear system, the trajectories will do something like this. Okay? Okay? So, of course, the system is also non-linearly unstable. So if you start nearby here, you're always going to go away, and you're going to go away via or to the unstable manifold of the fixed point. Okay? Now, and to compute this structure is a little bit laborious, but now think about it. How powerful is to know the presence of this unstable manifold? I know if basically you run all the trajectories you want in this system, you know that eventually the trajectory is going to settle into the unstable manifold and move with the unstable manifold. So that's basically telling us that you can just forget all the complexity of this equation and focus on this structure. The unstable manifold, and you know exactly everything about them. Because if you know where they are, wherever you start, you already know where they're going to end up, more or less. So this is basically a notion of coherent structures. You say, okay, you know what? I don't really care about all the possible complication of this differential equation, all the possible details of every trajectory that would start in different places. I just focus on these structures. Okay, those are basically examples of coherent structures. So these are basically the so-called asymptotic coherent structures, because to make sense, all of this, you have really to wait for infinite time. That's the way they've been designed. Okay, so there are basically some notions of asymptotic coherent structures. Fixed points is where you never move if you start there. The unstable manifold or the stable manifold of a fixed point, those are examples of coherent structures. because basically this is where things will go away or where things will go to the fixed point. And all these are important and have an impact on trajectories only if you wait for infinite time, okay? So now, guys, and this system is very trivial. It's just this simple, okay? Very different from, if someone, instead of, this is basically a velocity field. Do you realize it's just a velocity field in the plane? If you now simulate turbulence in 2D or whatever, you cannot call it turbulence maybe in 2D, but if you simulate a very complicated thing, how do you basically try to make sense of this complexity with these techniques? You cannot really do it. And the other thing I want you to basically draw attention is that, okay, all this construction that we did was looking at what happens in the vicinity of this point, near the fixed point. Okay, but now I ask you, hey, what happens if I start instead of the vicinity of the fixed point? What happens if I start in another regions of this domain, right? You don't know what happened because there are no techniques to address that. Instead, coherent structure will address that. We're going to learn basically that you can actually understand how things will evolve in this dynamical system, regardless also of where you start. You don't really have to be pinned necessarily in the vicinity of a fixed point or a limit cycle or other structures. Okay.
Can you just name the technique that you find nonlinear manifold?
Yeah, so basically, this is basically, so there are a couple of techniques to construct these manifolds, and they are based on basically the center manifold theorem. It's called. Basically, you compute the linearization of your dynamical system. If the linearization is basically, if the fixed point is hyperbolic, that means basically that the eigenvalues of the linearization have no zero real part, then you can sort of leverage some connections between the linearized dynamic and the nonlinear dynamics, and then build these structures. Okay. Okay. But is it clear? So basically, this is what would you do in the notion, in the case of very simple system. Let's say when someone gives you the equation, and when the system is time independent, this equation doesn't depend explicitly on time, and when you're interested on what happens over infinite time, okay? But then people I think like George were interested in understanding, okay, can I generalize these notions for any system that is also time dependent, and also when the system is defined via data set, right? Not really equations. Let's say someone doesn't give you the equation, you cannot do any of these constructions with the the existing techniques. Okay, questions? Okay. So basically, let me actually expand a little bit more the classification of coherent structures. So you have basically a time of influence. This is what we learned so far. So you can have basically short time. That means I'm interested in what happens over very short time. Okay, let's say search and rescue operation, optimal control of fluids, etc. You can also be interested in understanding what happens over a finite time interval, whatever it is, depending on the physics. You can also be interested in understanding what happens for t that goes to infinity. So here the asymptotic coherent structures. So basically they are here. With this is basically what I just showed an example. So eventually at the beginning everything started here, fixed point, stable manifold, unstable manifold, etc. And then people went back, really, also chronologically. So this is one axis of classification, and the other axis is the type of influence. Okay, so what is coherence for you? There are several types of influence, but at the beginning, the first three, I think, type of coherence that were basically initially developed in the group of George Haller were coherent structures of three types. One were kind of vortex type coherence, which is what you basically see in the asymptotic comparison. These are basically structures like limit cycles in classical dynamical system, and in this context you can think of these elliptic structures as basically vortex type structures. So these are basically regions that will basically start moving in the phase space and will stay coherent for a while. Okay. there are basically other structures which are called parabolic, which you can think of like jet-type structures. So let's say, for instance, Rossby waves or jets in the ocean. And the other ones that are perhaps maybe the most popular or the most frequent are attracting and repelling structures. They are together called hyperbolic, but this could be, where things will converge or where things will separate from. Okay, and I want to say that basically I can expand these axes pretty much in an unbounded way. There are different notions of coherence, for instance, synchronization, folding of fluid particles. It really depends on what you're interested in, and this is basically pretty much ongoing effort, in research. And the other thing is that I'm listing basically just 2 references, but of course there is a very big body of literature in this. So there is a review article from George Haller that has a lot of references, and I think recently George also wrote a book on coherent structure, so you can maybe look at more expanded version of these references there. Okay, yeah.
So this parabolic, that can you explain a little bit more? What is that structure type?
Yeah.
That part I didn't. It's elliptic and hyperbolic is very common.
Yeah.
We have studied a lot.
Yeah. So a jet, basically, think about when you have a very fast stream of fluid in the ocean. That's basically a jet-type structure. Okay, so you can think of a jet as a preferential pathway of transport. So, for instance, if you see in this context of, in the atmosphere, there are these waves that are called Rossby waves. Okay, these are basically, if you really put a tracer there and put a tracer in their vicinity, the tracer in the wave,
it's being transported.
But very fast. So there is basically, if you think of putting a bunch of tracers here, initially circular, after a while, if you see where these tracers are, they become of this like boomerang-shaped structure.
So basically, they will always travel. If you think about it, the tracers will always travel together. They will not like move away or come closer.
Well, there is gonna be deformation. There is gonna be deformation. That's why you transform this into a boomerang shape. But yeah, they will move together. But the way they deform is very peculiar. Okay. Yeah. I mean, so the mathematics of this, the way you redefine the structures is a little bit, also involved. But you can capture this using the finite time Lyapunov exponent, but not really, because they have their own definition. There are going to be ways to identify these jets, vortices, and attractors and repellers with the finite time Lyapunov exponent, but usually they have the so-called geodesic definition of this coherent. Yeah.
So this will parabolic. You will think, will there be a fixed point associated with it also for parabolic? So elliptic, hyperbolic, yes. For parabolic, will there be a fixed point?
There are basically, the interesting thing is that there are no fixed point in any of those. Because remember, that's actually an excellent point. So if you are basically in a system in which the dynamics is time independent, then likely you're going to have a fixed point associated with an attracting structure. But the beauty and the generality of these structures is that they exist also when things are time dependent. So in other words, basically, I'll give you a very simple example. If I deploy a set of, let's say that you put a bunch of points in the ocean, right? Okay, this blob of points, you know that the people deploy these little yellow ducks, and then they see how they spread, and after a while they go very far away. But let's say that you put these ducks, the floating ducks, in the plastic ducks in the ocean. After a while, this guy is basically moving, but also maybe he's doing something like this. So now you see the ducks disappearing this way. So this is going to be now, this is basically going to be an attracting structure, and that's instead a repelling structure. So you see that here there is no fixed point because everything is moving. The fixed point, nothing moves. But still, you can still have a very significant attraction and you can transform basically an area or basically an initial distribution of tracers from a spread out distribution to a very elongated distribution. Okay.
Yeah, so I see the point, but so it was easier to connect like this elliptic point and hyperbolic point from the analysis that one does, like in dynamical system for the autonomous system where there is no time dependence.
Yeah.
So you know that if it is a stable fixed point, it's more like elliptic point. If it is like saddle point, it's more like point. But parabolic point of connect from that point of view.
It's a good point. No, there is no easy connection for the parabolic one in that sense. Anupam.
Thanks.
Okay. All right. So let me actually give you a couple of examples. We are going to go back to these examples later in the course, but I'll give you an example of the polar vortex. So what is the polar vortex? So there is the Earth. Then there are different layers of air. It's very stratified, our atmosphere, and the polar vortex is basically you think about it basically as a cone that channels very cold air to the Earth's surface. Okay. And let's say, of course, there is going to be very cold air. The higher you go, the colder usually the air is. And then what happens basically in this, now 10 years ago, there was an exceptional cold in the east coast of the U.S., called Boston area, where that caused a lot of, casualties. Actually, people were dying. So at the beginning, it was unclear if this exceptional cold weather was caused either by air that was coming from higher altitudes, like cold air that comes from top and gets funneled down, or from cold air that was coming at the level of the ocean. So these are basically called North Atlantic oscillations, are basically very cold breeze of air that travel on the, on the surface of the Earth, on the, very close to the surface. And you wanted to understand where is this very cold air coming from, okay? Of course, this is the job of people that study atmospheric science, but what we tried to do here was, okay, there is available data set for the motion of air in the atmosphere. There are basically available data sets that are mixed from, models, very complicated, atmospheric models with a simulation of, measurements. You put basically sensor of temperature, local winds in different places. You integrate these two information and you have the most accurate way of modeling, atmospheric wind. So we said, wait a second, so if I have the atmospheric wind, now I have a dynamical system, and I want to understand if there is a very coherent vortex that deforms towards, so let's say the vortex is very, circularly symmetric when there was no cold, but then after a while, let's say this was basically 10 days later, after a while, this vortex is being pretty much deformed towards the northeast of the US. Okay, so maybe this view is not the best. And if that's the case, if I basically have a very coherent vortex that deforms, this vortex is going to carry the cold water. And remember, the cold, this cold air is just going to get funneled down towards the surface of the Earth. And that's basically what we were able to find. We were able to find that you can actually find this elliptic LCS over, a very significant height of the atmosphere that was actually initially spherically symmetric, and then it was actually deforming towards the northeast of the US, and whenever it gets there, remember, it's funneling down this very cold air. So this is a way to think that basically, there are a couple of considerations here. The first thing is that nobody was expecting that such a coherent vortex exists in a very complicated velocity field like the atmospheric flows, okay? And with these techniques, we're able to identify this vortex boundary. And then what you can also ask, guys, is that, okay, by this, is it really the vortex boundary, or is just a regions of highly coherent motion? To really understand if this is the vortex boundary, what you can do, you can say, okay, what happens if I step a little bit outside this boundary that I defined, And if I do that, so this is what I'm coloring here. So I'm coloring the interior of this boundary in blue, and then I have these little belts that I colored in different colors. And now I'm gonna play this and advect this with the flow. And the question is, if I would be just inside a very coherent region, they will all stay coherent. But if I'm really at the edge of a coherent region, they will be extremely, stretching and filamenting will be extremely irregular. And basically, this is what happens. So even in the same 10-day duration, you can see basically that although I stepped out very little, these little belts of material will stretch exponentially fast. Okay, this is basically a very strong case of exponential filamentation, and this basically is a strong evidence that these techniques are able to identify the edge of extremely coherent regions in the phase space. Okay, and this, from a dynamical system perspective, this resembles like the finite time versions of KM tori. It's not really important, but basically this is a Poincare map. If you know what it is, if you don't, it's not really important. But this is the way people were used to look for, coherent or elliptic islands in autonomous systems. So you do basically this Poincare map, and it's going to tell you that whenever you have this kind of circular structure that are nested with each other, those are basically the regions where things are coherent. When you see instead the very dotted or tessellated points is where the regions is chaotic. Now the question is, to do this, you need to have a system that is time independent, defined by equation, and defined over infinite time. Okay? With this, you can generalize these notions to systems that are defined by a data set, it can be completely time dependent, and also you can observe the effect of this, organization over, 10 days, because this is our time interval of interest. Okay, so, this is what, yeah.
Maybe I haven't understood properly, but this simulation, does this mean that there are multiple layers of?
Yeah, there are multiple layers. So basically, what happens is that the air is, so this is not, it's basically a mix between simulation and assimilated data. This data is available online. So if you go to the paper, there is basically the place where we got the data. There are basically these atmospheric models. But yeah, the physics of it is that the data, so the velocity field in the atmosphere is pretty much stratified. So there are basic layers over which most of the dynamics is happening. Okay, and then of course there is intra-layer dynamics, but most of the dynamics is basically stratified. Like in the ocean, there are basically stratifications of constant density. I don't remember what is basically conserved in any layer, but yeah, most of the dynamics is basically in this constant something layers. But then there is going to be also regions where you have a lot of subduction or upwelling of fluids. That's why you can see them at different layers. Yeah. But that has nothing to do with the technique. Okay, that's just one way. Okay, so I'll give you another example of this basically coherent structure. So in these other, yeah.
So basically, there is not. So most of the dynamics is only in some sense XY plane, right? Not much.
Yeah.
Transferring the theta because of the density difference. These are stratified flows.
Yeah. So it's not really the density. This is, I think, is called they are basically isentropic surfaces. Now I don't remember exactly what's conserved. It's not necessarily the density. Like in the ocean, it is mostly the density. Yeah.
Even in atmospheric, you can have different layers based on the density. So basically, if there is a gradient along z in the density, so it can be treated as two-dimensional, layer by layer.
Yeah. But the problem is that when I was looking at this, actually in the data set, there are data at different layers. Could be density, could be potential temperature, etc. Then the question is, if I observe fluid tracers, particles of air, where are the most two-dimensional? And in the atmosphere was not the density, was something else. I don't know. There was some other constraints that the potential temperature was. Okay. So this is basically, if you will now, if we go back to the previous, classifications or attempt of classification, this was basically finite time vortex type coherence. Okay, but another example, again, we're gonna look at this more in detail later this week, but it could be search and rescue. This could be basically an attractor that you need to identify that is important over a very short time. So this is now Eulerian, or short time, attracting type structures. And why this is basically, why do you want to look at things over a very short time? Is because if you talk to people at the Coast Guard in the US, and I think pretty much everywhere, to identify where people will accumulate, if you don't do it within 6 hours, it's very likely that you just have to recover these people. It's not going to be a rescue mission, but it's going to be just finding dead bodies, unfortunately. So you want to be very quick, and you have very limited assets available. So whenever there is a search and rescue operation, you have a couple of helicopters and 2 boats. So with this, you want to understand very effectively where should you go, okay? So in this case, what we did, we said, okay, what's really available to the Coast Guard? The Coast Guard, when there is basically an accident, there is a so-called point of last seen, which is where you observe the plane, or the plane communicated with radio to the, the central, the tower station. It was basically one particular point, and then you say, okay, since then, I don't know, there is, this happened an hour ago. So from that point of last seen, you draw basically a circle and say, okay, how fast ocean currents are, and then you say, this is my area of uncertainty, okay? And the more you wait, the more it grows, okay? And so what happens? The Coast Guard uses velocity field that simulate basically the ocean surface dynamic. In different regions of the globe, there are different models. Every model is more optimized for one particular region. Why? Because they tune the parameter for that particular region. Is it close to the coast? It is in the middle of the ocean? Do I have sensors in the vicinity of this region, so that, if I have buoys, if I have, temperature sensor, etc., they will, integrate this measured information into the model to reproduce a better estimates for the velocity. So that's the input for the Coast Guard. And of course, there is a lot of ranges of uncertainties. There is variations in wind, the shape of the objects that are basically floating, etc. So what we said, okay, we want basically to identify, to see if these structures like traps, or the attracting objectively current structures, which is if you will, short time attractors, can they actually help identify where things will accumulate? And that's what we did, basically. Again, we are going to discuss this in detail later in the week, but we started basically, this is Martha's Vineyard, so Boston was somewhere here, so Anupam and I were here. This is basically an island off of the east coast of the US, and this is where we did these field experiments, basically. So we were just targeting this area, and we were using the ocean surface velocity field, so the velocity field that the Coast Guard has, and then with boats, we were actually going here and saying, okay, let me deploy drifters, just very big buoys and mannequins, and put a GPS on top of them, and then see if they will indeed go where these short-time attractors are. Okay, if they go there, because I can track them with GPS, then that means it's a good prediction to understand where things will float. And that's basically what we did. Again, we are just going to do this very briefly, but we're going to expand this explanation later in the week. But this is what happens. You have a bunch of these buoys that are in the water, 70 of them. And this is the streamlines of the instantaneous velocity field that I just told you. So this is basically a very spread out distribution of buoys. Think of this as floating people, okay? And after basically 2 hours, you see that there are these traps, which is these short-time attractors that are emerging. Again, the way to read this is that the more negative you are, the most attracting you are. And these regions, the red is the directions where things will get attracted. So it's really exactly this, right? So this is basically, think of this line as a red line, Okay, and the strength of attraction really depends on the scalar field. The more blue you are, the more attractive you are. Okay, so this after 2 hours from this spread out distribution, I would start converging into this basically streamline structure, and in 3 hours it's even stronger. Okay, and the interesting thing here is that this is the underlying streamlines of the velocity field. So basically, Anupam, there is no fixed point here. There is nothing. Everything is actually drifting because there is a current, but still, the gradients of velocity are such that you create a very strong accumulation of floating objects in this region. Okay, of course, it's way more complicated, but the way to, intuitively understand it, think about that you have basically in a channel, you have velocity field 0 point in this direction, but here you go much faster than here. Okay, so if I observe something here, of course, I'm gonna see an accumulation region here that is still gonna move, but still this is gonna accumulate, a lot of material there, and of course, this after 3 hours, people, maybe the reviewers were saying, look, is this just a matter of looking at the planar divergence of the velocity? Not really, because this is what we computed from the velocity field, and you can still have basically attraction where the divergence of the velocity is 0 or positive. Okay, so it's basically a little bit more. There are a lot of possibility that can generate basically these short-time attractors, and we just expand them in the paper. Okay.
Is it two-dimensional divergence or
2D divergence? Yeah.
Because the flow is incompressible.
Fluid is incompressible. Good point. Yeah. So the fluid is incompressible. This is the two-dimensional divergence, which is what is important if you want to understand where things accumulate on the surface. Yeah. Okay, so this is just another example. I don't know, how much time do I have?
I think we can stay here. So maybe, so do you want to continue? So we can continue after tea break, or how do you want?
No, let me actually, I'll get maybe 5 more minutes to give a general, okay. So the first thing is, okay, why do we actually need to do all this instead of basically looking just at velocity or vorticity, right? Which would be much easier to do. So think about this. So if I give you this velocity field, the time 0, 0.5, and 1, what would you guess? So, okay, is this a vortex? Yes, because you see, this is a good thing. So you think it's a vortex because you think that just looking at, circular patterns, if you will, of the streamlines or the velocity distribution implies a vortex. I mean, that implies a vortex only if you have that the velocity field is time independent. But these are time-dependent velocity, like in the ocean. So that intuition that you have for thinking vortices as basically, regions where you just have closed streamlines breaks down when the system becomes basically time-dependent, okay? And in fact, this is what happens in this system. So I start with a bunch of particles here, and I let them go after one time unit, which is very little, and I actually, instead of really seeing a vortex that keeps particles together, these particles are actually exponentially stretching. So this patch of material is exponentially stretching. So basically, this is what happens. Okay, so things rotate, but this is basically, it's actually a settled point that is rotating. So it's the opposite of a vortex type coherence. Is an attractor plus a repeller that are rotating. So this is basically to say that when things become time dependent, the intuition that we had from time-independent flows, you have to be very careful in using them, and especially, for instance, if you want to use to save people. You have to be very careful and trying to understand, whatever we showed so far and whatever we're going to maybe show in this course is that we are going to look for structures that attract material, that repel material, that keeps material together. And the reason why we cannot just look naively at velocity plots is for this reason, that when the system is time dependent, the velocities, or just having closed streamlines, has no predictive power in telling you how things will evolve. Okay, because these streamlines are time dependent; they are not just trajectories. The same, you can also do it with the Q criterion or the vorticity. I mean, maybe I just skip here, but this is basically the ABC flow. The Q criterion is basically a criterion that is spin minus strain. Whenever this scalar field is greater than 0, that means it's a vortex type structure. So this shows that these regions is basically a vortex type structure. Right, so basically this is where Q is equal to 0. So if you are in this particular system, that regions of the flow should be a vortex type structures. However, this is not the case. I mean, when we compute the finite time Lyapunov exponent, we see basically that the regions that is a vortex type structures is this. While if you think about this area, you're just basically here where you have very positive, actually positive Lyapunov exponent. So basically this is telling you that the vortex is in the regions where I'm going to have exponential separation. Same story for this system, and if you want to have the ericity, there is no other technique that can tell you where things will stay together. And just this is an overview. If you animate this structure, basically you can see that the structures that are here, they will stay together. That's why the green particle will always stay here confined. But if you are here, for instance, let's say in this region here, if you are here, this gray particle will just fill all this domain. There's going to be very much a chaotic regions or exponential separation. So this is again, vorticity and Q criterion will not be able to tell you where things behave, in a material coherent way. I think I'll skip the frame invariance and one last thing, which is also related to some stuff that I discussed with Anupam, is that what happens when you're interested in things that accumulate or get attracted or repelled that are not necessarily fluid particles. Well, we already saw an example before with buoys. Okay, so that was basically, we already knew. I said, okay, can I identify structures in the flow where basically I can predict the accumulation of floaters, so I can see very robust attractors in the flow, short-time attractors in the flows that not only attract fluid particles, but will also attract buoys or mannequins, okay? But if you know more about the nature of this non-fluid flow part, then you can also generalize the notion of coherent structures. And let me actually go back here to this video. This is basically a video from the group of Howard Stone. It's a very cool thing. So this is basically a T-junction where fluid comes in and the half goes right, half goes left. But so if you would just put fluid particles here, there is no accumulations. There is no accumulation. Half goes left, half goes right. But Howard, I think, was putting bubbles. And the fact that those are bubbles immersed in this fluid and not basically fluid particles basically generated. Yeah, thanks. Yeah, so they generated basically a very invisible attractor. It's basically a floating attractor. It's crazy. Just because these guys are bubbles, they are not just fluid particles, you can generate a very basically unexpected attractor here. And this is to say basically that if you now start tweaking the definition of dynamical system with fluid contribution and some non-fluid contribution, you can predict all these structures. Okay, and this basically is very relevant, for instance, for arteries, etc., because there are a lot of floating things in our bloodstream, and this if you have these attractors, you can create clogging, etc. So basically, just a little bit to generalize. This is
So those are like naturally hyperbolic points, like they go and then they.
I mean, what is an hyperbolic? There is no hyperbolic. So if you really plot the streamlines of the fluid, I mean, there is very little that exotic here, right? I mean, now there's going to be some flow profile. It's not so important here, but basically that's what happens. But okay, so I have this, but there is no, I would never expect in a tractor an accumulation of thing here. In fact, if you put a die, there is nothing that really accumulates there. But the fact that you're gonna have bubbles and not fluid particles is gonna be key, because that little modification can create some attracting structure. And most of the energy and the activity is coming from the fluid. But the fact that you're not just gonna be a fluid particle, but something else can create very different, coherent structures, if you will. And this is something we are doing basically in the group, which is the following. It's basically just a generalization. I don't know if some of these definitely people are already explored. I mean, I think Kevin Mitchell at UC Merced has looked at some of these structure, Tom Solomon, etc. But in general, you can cast the following problems. You can have an ambient flow velocity, which I'm going to mark with V fluid. And then, this is the dynamical system of the fluid. And then basically think about some, either, particles or microorganisms. This object that is not going to be a fluid, because the fluid would obey this differential equation, is going to be, the particle, the velocity of the particle is going to be some velocity of the fluid at the position of the particle, plus some little correction. Okay, which I'm going to call with F, and this epsilon is a small parameter, okay? And then P is basically what people call taxis. It's basically, okay, this P is going to be some function of the particular properties of this microorganism or of particle velocity. And then you can ask, can I now, knowing the velocity field of the fluid and this interaction, can I now understand in this given flow, where do things accumulate that are not fluid particles? And this could be, for instance, bacteria, they could be fish, they could be inertial particles, they could be, everything you want, right? And, this, for instance, you can use it for understanding where things accumulate in the, in the atmosphere. People were looking at, a few years ago, people were looking at, solar geoengineering. So they were trying to, put some sun reflective particles in the atmosphere to limit the ozone depletion and stuff like that. This is one example of that. When you have a very small microorganisms or fish, these fish are basically moving in a fluid, but then they also have their own dynamics. They could be responding to shear, the so-called rheotaxis, or they can respond to light or other things, right? So you cannot cast this in this language and then say, okay, because I know the fluid velocity, where would I find most likely this type of species? Or I don't know, how could I, for instance, design the fluid velocity so that the distribution of the particular, particles are the ones I want? Okay, so this is basically a synergy of leveraging the coherent structures for the fluid with this little, interaction, additional piece of dynamic that is very much associated with the particular, particles or microorganisms. I think that's what I want to do. I mean, this is basically, okay, something is happening. I think that's all I wanted to convey. I mean, there are many other type of coherent structure. I think you got the flavor of it, and that's it. I think I'm just gonna stop here and take more questions, or during the break now, whatever you want. Okay.
Okay, thanks.
Yeah.
So of course, Mathieu is around even during the tea break, and we'll take a tea break.
Yeah. Thank you.